Welcome to our very short discussion on related rates. So let's say you're pumping air into a balloon. It's obvious that both the volume and the radius of the balloon are going to increase, and that those rates of increase are somehow related to each other. But it's going to be much easier to measure directly the rate of increase of the volume, right? Because if you know like how much air you're putting into it, then the rate of increase of the radius. But if we want to know how fast the radius is changing, we can figure that out by relating it to the rate of increase of the volume. And that's the idea of a related rates problem, is we can relate those two rates of change together. And then using the chain rule, we can differentiate both sides with respect to time and solve one rate for the other. Let's take a look at an example. So we'll go back to that spherical balloon. Air is being pumped into it so that the volume increases at a rate of 100 centimeters cubed per second. Again, that's an easy thing to know because you know how fast you're putting air into it, and so that's the rate of increase. And then we want to know how fast is the radius of the balloon increasing when the diameter is 50 centimeters. Now you should always start these things off by drawing a picture. Well, there's not really much of a picture you can draw with a balloon, but maybe you give yourself a picture of a circle and think about the radius, and as that increases, so does the volume, in this case area if we're looking at a circle. And then you identify a couple things. You want to identify the information that you're given, and you're given the rate of increase of the volume. And then you want to identify what you're looking for, and you're looking for the rate of increase of the radius. Now, in order to express those quantities mathematically, you're going to have to start labeling some things. So we're going to go ahead and let capital V be the volume of the balloon, and R, little r, right, be the radius. And the key thing to remember here is that rates of change are derivatives. And so in this problem, the volume and the radius are both going to be functions of some time t, and then the rates of increase of the volume and the radius are simply going to be the derivatives of those functions, dv dt and dr dt. We can then restate what we're given and what we're trying to find in terms of derivatives, right? We're given the rate of increase of the volume, that's a dv dt, and we're trying to find the rate of increase of the radius when the diameter equals 50, but when the diameter equals 50, that's the same thing as radius equals 25. But that rate of increase of the radius is just a dr dt. And so we're given a dv dt, we want to find a dr dt, and now what we need to do is connect those two pieces. We need to somehow connect the dv dt to the dr dt, and really that requires coming up with an equation that relates v and r, and then we'll take the derivative, and thus we'll get dv's and drs. Well, the easiest, most hopefully obvious way to relate those is with the equation for the volume of a sphere, which is just 4/3 pi r cubed. Now we know that using the chain rule, dv dt, right, the change in volume with respect to time, is equal to the change in volume with respect to radius times the change in radius with respect to time. So with the original volume equals 4/3 pi r cubed, if you want to take dv dt, right, you're basically taking d dt of both sides, the derivative with respect to time. That's where you get dv dt here, and then you're going to get a dr dt over here. So the 3 comes down and cancels that, and that's where you get the 4, and then pi r squared dr dt. Now we can solve for the unknown quantity. If we have dv dt equals 4 pi r squared dr dt, this is what we're looking for. We're trying to find the rate of change of the radius with respect to time. This is what we're given. They told us that that was 100. And then they also told us when the diameter was 50 or the radius was 25. So algebraically, you can solve for what you're looking for, this piece, by moving everything else to the other side of the line, and that's where they get this. All right, plug in what we know. We plug in the 25 for r, the 100 for the dV/dt, do some simple math. You get 1 over 25 pi, or roughly 0.0127 centimeters per second. Why is it centimeters per second? Because that was the rate, right? This was centimeters cubed. This was in centimeters. Centimeters cubed divided by centimeters squared leaves you with centimeters, right? Centimeters cubed per second, so you now have centimeters per second. So it's always a good idea to keep track of the rate of change. All right, one more example. You have a 10-foot ladder. It's resting against a vertical wall. If the bottom of the ladder slides away from the wall at a rate of 1 feet per second, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? Well, step one, draw yourself a picture. So here's your simple picture of the ladder leaning against a wall. You always want to draw a picture whenever you can, and then label what we know. We've got an x distance, a y distance. They tell us the rate of change in this direction. Dx dt is 1. We're looking for dy dt. And then what else they tell us? Well, they told us when x equals 6, this is still 10. Now we have a picture of everything we know, everything we're looking for. Step 2 is to take what we're given and figure out what we're trying to find, right? We were given this rate, we're trying to find that rate. So now we have to find an equation that relates those two things. We need to somehow relate x and y, and it should be very obvious that good old Pythagoras will help us with that. We know that this is a right triangle, so x squared plus y squared equals, right, the hypotenuse squared, which in this case is 100. That's 100, not 100.1. I don't know where that is coming from. And then if we differentiate both sides with respect to t, we get this simple thing, right? If you take the derivative of this with respect to t, you get 2x dx dt plus 2y dy dt equals 100. Remember, we're taking the derivative with respect to time because we want to know these rates with respect to time. And when you're taking the derivative of a variable with respect to a different variable, that's implicit differentiation. And you take the derivative like normal, you just have to have that d blank at the end. In this case, it's dx dt and dy dt. Okay, well, now that we have that simple formula, 2x dx dt plus 2y dy dt equals 0, we plug in everything we know and solve for what we don't. Well, we're trying to figure out the rate of change of y. So we want to solve for y, and algebraically it ends up being this. Now, you don't have to do this algebra if you don't want to. It's actually very easy algebra to do, right? If we're trying to solve for dy dt, first thing you do is move that over to the other side. You get 2y dy dt equals negative 2x dx dt. Then you divide both sides by 2y, right? That's where the 2's cancel, and that's where you get negative xy dx dt. But you don't need to do that because you can just plug in everything that you know and solve for what you don't. Now, where did the y come from? Well, that came from Pythagoras' theorem. If you go back and look at your picture here, right? If this is 6, this is 10, we can solve for y by having 6 squared plus y squared equals 10 squared. 36 plus y squared equals 100. Y squared equals 64. Y equals plus and minus 8. But of course, minus 8 doesn't work, right? Because you can't have a negative 8 distance. And y equals 8. And that's where the 8 comes from. Well, you plug in the 6 for x, the 8 for y, the 1 for the rate they told you, right? The bottom of the ladder, the dx dt was moving at 1 foot per second. You plug all that in, and you get the top is moving at negative 3/4 feet per second. Now, if you didn't do this algebra, you didn't solve it here, and you just used this formula there, you would have got the same thing, right? Plug in everything you know. You would have 2 times 6, right? Because there's my 2x, and then dx dt is 1 plus 2 times y dy dt equals 0. 12 plus 16 dy dt equals 0. 16 dy dt equals negative 12. Divide by 16, and dy dt equals negative 12 over 16, which is negative 3/4. Same thing, okay? So you can always just do the algebra at the end with numbers if you don't want to move around things and solve for dy dt. Okay, does it make sense to have a negative? Right, that the rate of change of y with respect to time is a negative 3/4 feet per second. Well, of course that makes sense because the ladder is sliding down the wall, and therefore it's going to have a negative rate. When we're talking about rates of change, direction does matter. Okay, in summary, to do a rate of change questions, it's really simple. Step 1, draw yourself a picture, label what you know. Step 2, determine what you know and what you don't know, i.e. what you're trying to find. And then from that, you can go to step 3, where you have to find an equation that relates the known variable with the unknown variable. In the previous example, we knew the distance x, we didn't know the distance y, right? We knew the dx dt, but we didn't know dy dt, so we needed something that related x and y. In the first example, we had an r, we had a dv dt, we needed a dr dt, so we needed something that related the v and the r, and thus we used the equation for volume. It's just that simple. You'll always come up with an equation that relates the two variables, and then therefore when you take the derivative, it will relate the two derivatives. So then you take the derivatives with respect to time, solve for the unknown that you don't know by plugging in everything that you do know, and Bob's your uncle. It's that simple.